Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with our lesson for today, chapter 9.1.2. We're going to start exploring how to find the area of a circle. As you may recall, when you find the area of any shape, you're trying to find the number of square units that fit inside that shape. And when you have shapes like rectangles or squares, it's really easy because you've got these whole squares that can be counted. So this rectangle is 4 units high and 6 units wide. 4 times 6 is 24. So when you go through and you physically count the number of square units on the inside, you will see that there are 24 of them. Triangles a little bit trickier because with a triangle, you've got some of those partial you've got some partial squares in here, but it's a fairly easy workaround. And we learned that there's a formula for the triangle where the triangle is exactly 1/2 of a square or rectangle. Actually, let me go ahead and just do a square here. It is exactly 1/2 the size of a square or a rectangle that has the exact same base and height. And so if you can count up the total number of, come on, there we go. OCD taken over here. If you can count up the total number of squares that you would find in this rectangular square, then cut it in half, then you've got the number of square units inside this triangle. Well, this is not so easy with circles. With circles, if I'm going to try and count the total number of square units, there are 4 of them that are complete, but the rest of them are partials, and this one's almost 1. How much is that? This looks like it might be a little bit less than half of a square. So it gets a little bit trickier with the circles. So this lesson is not immediately going to show you the formula, which there is a formula for finding the area of circles. We'll get to that in day 2, and we'll explain why that formula works. There's a pretty cool tool on your online book that allows you to see how you can transform a circle into a square or a rectangle, and a rectangle into a circle. It's pretty neat, but we'll get there. We're getting ahead of ourselves. In the meantime, today we're going to explore some different strategies that have been used over the years when people didn't know the formula and they had to come up with some other strategy to figure out what the area, the number of square units fitting inside of a circle. All right, so the ratio known as pi was first discovered by the Babylonians about 4,000 years ago. Over the years, Egyptians, Chinese, and Greek mathematicians also found the constant ratio between the circumference and diameter of a circle by using measurement. Okay, so just so that we remember, we learned that circumference is equal to pi times the diameter. We learned that in lesson 9.1.1. And basically, I get this question all the time. How did they figure out what pi was? Well, if you divide each side of this equation by the diameter, you end up with the circumference divided by the diameter, but then this cancels out with the giant 1, right? So that cancels out, leaving you with the circumference divided by the diameter gives you pi. That's a very nice pi symbol there. Looks almost like a set of antlers there. Let's start. Okay, there you go. All right. So the Greek letter pi has been used to represent this ratio since the 1700s, when it was made popular by a Swiss mathematician named Euler. Even though the ratio has been known for many years, the value commonly used for pi is still only approximation. So it's one of those, what we call an irrational number, where it just keeps going on and on forever. And they're actually mathematicians who've made it their life quest to figure out the next decimal digit in pi. Everyone's got to have a hobby, right? So they like to do that. All right, so a circle is different from any shape you have studied so far because it has no sides or corners. This makes it difficult to apply the strategy for decomposing, that is, breaking it into parts, finding out the area of the parts, and putting it back together like we can for like triangles and trapezoids and some other complex shapes. In this lesson, estimating its area can be a useful technique. I have put this resource page, which you could find on the online book. If you just wanted to click it, it's a PDF file. You could print it off and do it. I've also put it on Classroom if you chose to print it off. If you don't have a printer at home and you just want to watch me do the work, that is totally fine. So using the first circle with a radius of 5 units on the resource page, estimate the area of the circle by counting the whole parts and the part squares, or counting the whole squares and the part squares. You're not going to have a team to do it, so we're not going to be able to compare with other team members, but this is what it looks like right here. So if you've got the means, go ahead and pause the video right now and go see if you can print this off, so you can do it along with me. But if you don't plan on doing that, then don't bother pausing. I'm going to move ahead right now. So now's the time to pause or just watch me. So they say that this circle has a radius of 5 units, right? And you can see, 1, 2, 3, you can count it on the coordinate grid that this is laid over top of. And it really wouldn't matter. See if I can grab it. There we go. It wouldn't matter if we were going to that point, if we were going to this point, if we were going to this point. This circle has a radius of 5 units, regardless of what part of the circle we put it on, okay? So with that in mind, the directions said to estimate the total number of squares on the inside. So I'm going to literally count all the complete squares here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. That's not complete. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. I'm going to say that there are 60 complete squares there. Now, I'm going to go to the ones that look like they're almost a complete square, because all we can do is estimate, right? So can we just call that a complete square, even though there's like that little sliver there and there's a little sliver here? So that's 1, 2. Actually, let me change colors a little bit, just so I can coordinate this better. Green will do. 1, 2, 3, 4, 5, 6, 7, 8. All right, we're going to call those complete squares. Now, see that little sliver right there? Does that match up with any of these parts in here? I'm not really sure. I'm going to say that looks like a half, right? So let's go 1 half there with 1 half there. So that's 1. And then 1 there and 1 there, and that makes 2. And could those two combine almost make 1? I think they will. So we're going to combine those two and these two. That's 1, 2, 3, 4. And then how about here? What do we have left? All right. I'm just going to count that as 1, 1, 2, 3, 4 more. Okay. So that's going to be as good an estimate as I think we're going to come up with. You go ahead and do your counting and see if you don't come up with the same number that I came up with. So let's see. We've got 68, 70. Does that look like it's about 78 square units in there? All right. So you could do that, but I don't know how accurate that is. Counting those up completely. You remember there were some of those in there, which I'm not real confident that these two combined made 1, but it was close. And since we're just doing an approximation, okay, we'll see if that works. Okay. All right, so that was problem number 22, correct? All right, now let's get into the meat of this lesson today. While it is convenient to estimate area when shapes are drawn on a grid paper, shapes are often not presented in that way. How can other shapes be used to help estimate area? So look carefully at the shape at the right. Do you notice what we have here is we've got a larger square on the outside, and we've got a smaller square on the inside, and the circle fits inside the larger square. Remember, the radius here was 5, right? So we can use that radius double it to make the diameter, which also matches up with the diameter, um, which is also the side length of the square, right? So how can you find the area of the larger square? What would you have to do there to figure out what the larger square is? What I would like for you to do, pause the video, read through each one of these questions and see if you can formulate a response in your head. Some of them you might be able to get without too much trouble. Others you might need to think about it a while. Some others maybe you don't know the answer. But it's good for you to think about this. So pause the video, see if you can come up with an answer, write it down in your journal, and then when you come back, check and see if your answers match mine. If you're completely off from what I say, scratch it out and copy down what I have written in. If you're not certain and you don't want to write anything, you just want to wait for my response, that's okay too. So go ahead and pause and then come back when you're ready. All right, we'll assume you just did some great work, or you just paused with me and now you're ready to move on. So how can you find the area of the larger square? What is the area of the larger square? If you said that the diameter of the circle is the side length of the square, and that means that 10 times 10 gives you the large square with an area of 100 square units. You did a great job. Good job. Now, how can you find the area of the smaller square? This is going to be a little bit trickier. The smaller square, we don't know that side length right there, right? But we do know this. We do know that we could create, let me make a little dotted line here. I'll do this one right there. We could create 4 right triangles in there. And each one of those right triangles has known dimensions, right? This is 5 because that's the radius, and that's 5 because that's the radius. So how do you find the area of this triangle right there? Base times height, and then divide it by 2. You could also just take this whole triangle here, which has a base of 10 and a height of 5, and so that would be 50, and you cut that in half, and that's 25. So I believe the top part is 25, which means that the lower part would have to be 25 as well, right? So what I said here was find the area of each quarter and then solve the problem. So you got 4 quarters, and so that'd be half of 25 times 4. I guarantee you it's going to end up being 50 square units. So how does the actual area of the circle compare to the area of each square? Well, notice how the circle is bigger than the small square, and it's smaller than the largest square. So it's got to be somewhere in between there. So I think a good estimate would be like the halfway point between there, which would be somewhere around 75. Do I even have that written in there? I guess maybe I don't. But it says the area of the circle is between those 2 areas, but I'm going to guess it's about 75, okay? So discuss with your team how to use both areas to estimate the area. Well, this is basically what I said. I said find the average of the 2 areas. And so the average of the 2 areas have to be 150, 100 plus 50 divided by 2. So it's going to be about 75 units. Now, 75 units using some mathematical logic. I believe they call this, the inside-outside method. The inside-outside average method. And how close did we come to my estimate here? I thought it was going to be about 78 by just doing some counting. But I don't really have an idea if this is over the actual area or if it's a little bit less or how close it is. Either way, to be within 3 square units by using 2 different strategies, I think is pretty close. And so my guess is that the area is going to be in that high 70 range, somewhere in there. All right, so Julia needs to estimate the area of a circle that has 6 units as its radius. She decides to use the inside-outside method to make her estimate. So on that resource page, let's go back here. Here's the resource page. When you go down to the second part, what did we say here? We already did part A, right? So this one was about 75 square units. And now this one, wait, I don't know. Are we doing the same one? Hold on for a second. I'm confused. That was 23. Now we're on 24. We have a different resource page. Oh, there it is. Okay. So we're going to move forward. So once again, this is a second resource page that you're going to have to use. 9.1.2a. Is this on the back side? I don't know where this is. At any rate, hopefully you'll be able to find it. If not, just watch what I'm doing. So now we're going to use this inside-outside method to solve for a circle that has a radius of 6 units. Okay, so let's actually, why don't you go ahead and pause it. I'm going to pause it, and I'm going to use a little strategy here. When you come back, see if your strategy matches mine. All right, so I have not finished my answer yet, but this is what I did. I decided, since the diameter is, the radius is 6 units, the diameter must be 12. That means that this larger square has to be a 12 by 12 square, so it has 144 square units. I then sort of pictured what the square would look like on the inside, and I actually drew it in. And so just like with the previous example, we end up with 4 right triangles that have a height of 6 and a base of 6. I combined the upper into a triangle that was 6 by 12. So half of 6 times 12 is 36, but then you've got this guy, that's 36 square units, and we're going to double it since that's exact the same. So the total square is going to be 72 square units. So that means that the area of the circle has to be between 72 square units and 144 square units. So let's come back to these questions here and see what we have written down here. It says, how are the length, width, and area of each small square related to the radius of the circle? So I stated the radius of the circle is the side length of each smaller square and half the side length of the larger square. I wouldn't actually, I think that's a little bit wrong. The radius of the circle is the side length of each of these small small triangles. Let's say triangles in there. You go ahead and write that in. And so what do we have here? Julia divided the side square into the inside square into triangles. How is each triangle related to the radius? How is, yeah, I don't feel like going into that. I got a headache and this is bugging me. But the base and the height of each triangle is the same as the radius. Okay, so that's kind of what we were getting at there. And what else does it say? The area of the small square is equal to 2 times whatever the radius squared is. Well, that's interesting. I didn't think about that at first, but you know, that's work that I'd done in previous years. But yeah, the radius squared is 36, and then you double it, and you've got this measurement there. Was that the same in the previous example? Yes, it was. You take the radius and you square it, and then you double that, and that ends up being the area of the circle on the inside. All right, well, you know, you do these long enough and you start to discover things that you had forgotten about or never discovered before, but obviously I had figured that out once before. All right, so if the area of the two squares is related to the radius of the circle, Julia wonders if she can relate her circle estimate back to the radius as well. With your team, look at the estimate. You don't have your team here, so let's just see what I've got written in here. So what do we have here? Starting off here, the area of the circle will be between the area of the smaller square and the area of the larger square. Okay, so we know that. What comes next? The smaller one we decided was 72 square units. The larger one was 144 square units, which means that if we use the averaging method, what is going to be the approximate area of this circle with the radius of 6? Well, if you add 144 plus 72, you get 216, and half of that is 108. So I believe that the area of a circle that has a radius of 6 units is going to be 108, approximately 108 square units. All right, and that ends today's lesson. Tomorrow, we are going to get into the formula, and you're going to be able to use a calculator to figure out how to find the area of all circles. Go ahead, please do your homework. Please practice this inside-outside averaging method. It is actually a pretty useful tool if you understand how to find it. If you don't have a calculator, if you're going to use pi and you're going to start squaring things like the formula is going to have us do, not having a calculator, it can get a little bit tricky sometimes. So this is a good method if all you need is a good estimate or an approximation. All right, good luck on your homework, and we'll finish this lesson tomorrow.
Hey, feeling good, like I should. When in dark, walk